In the first 30 seconds of Mission Impossible Ghost Protocol, a doomed IMF agent is running across the roof of a tall building. He's trying to get away from two bad guys, a favorite pastime of all secret agents. In his right hand, the agent has a small object, an object that is about to get very big and very important. The agent is holding crash pad in a can. Watch what happens. Crash pad in a can? Is there any way this could work? Let's first see if a simple expansion of compressed gas, say from a big CO2 cartridge, might do it. The volume of the object in the agent's hand, what I'm calling the can or canister, is no more than 1 liter. Here's a 1 liter Coke bottle to give you an idea of how much volume that is. Oh, I'm sorry. This is a 1 liter bottle of Diet Coke. Of course. While 1 liter is a handy unit of volume, it's not the international standard. Around the world, in every corner of planet Earth, except the corner shaped like this, the official unit of volume is the cubic meter. Three-dimensional creatures, and I qualify, barely, should be familiar with the cubic meter. It's the volume of space inside a large refrigerator. So 1 cubic meter of air would fill an otherwise empty home refrigerator. We need to be familiar with the cubic meter in order to estimate the volume of the inflated crash pad. To the nearest power of 10, the volume of the crash pad is 10 cubic meters. Look at the volume difference between this 1 liter bottle and the 10 cubic meter crash pad. How does this become that? 1,000 liters fit inside a cubic meter. 1,000 of these will fit in a big refrigerator. We'd have to do some cramming, but they'd go. The 1 liter object in the secret agent's hand has to increase in volume to 10 cubic meters. From this to 10 refrigerators? That's a volume growth factor of 10,000. Can you imagine what incredible pressure of stuff just itching to get out there must be inside such a can? Well, we can do better than just imagine. We can figure the pressure out. Let's do something very generous for the makers of Ghost Protocol. Let's assume that the 1 liter object in the agent's hand contains nothing but gas that can expand. Let's ignore the fact that the plastic skin of the crash pad has to fit in the can too. Let's suppose that the crash pad skin is so light, so strong, and so very thin that it magically takes up none of the space in the 1 liter can. Let's make the situation ideal in another way too. Let's treat the gas that inflates the crash pad as a so-called ideal gas. Then we can turn to the law that describes the behavior of an ideal gas. You know what it's called. You learned it in high school. It's the ideal gas law. PV equals nRT. Pressure times volume equals the number of moles of gas times the gas constant times the temperature. But wait, I'm not a chemist. I'm a physics teacher. So I'll use the physics teacher version of the ideal gas law. That's P, pressure, equals nKT divided by V. Capital N is the number of atoms, K is Boltzmann's constant, T is the temperature, and V is the volume. Why might this be better? Because now the ideal gas law describes cause and effect. And you can get a feel from the equation itself why the law is true. The effect is, again, gas pressure, P. And there are three causes of gas pressure. First, the number of gas atoms, capital N, that are flying around. Second, the energy of each atom's flight, kT. K is known as Boltzmann's constant, and T is the absolute temperature. And finally, the volume of space in which the energetic atoms are confined, capital V. It makes intuitive sense. Intuition cannot prove a law, but it sure can help us remember it. Pressure is caused by a number of atoms, each with energy confined in a volume. P equals nKT over V. The ideal gas law, it's important, it's worth remembering. Very useful law in watching good movies and in breathing. Notice the volume capital V in the ideal gas law is in the denominator. This means that the pressure varies inversely with the volume. We don't have to worry about N, K, and T in this equation because they're not changing. The number of atoms, their temperature, and of course Boltzmann's constant all remain unchanged. That's because the atoms in the crash pad all came from the can, and both the can and the crash pad remain more or less at the same temperature. So, the ideal gas law is telling us that the pressure varies inversely with the volume. For example, if the volume doubles, then the pressure is cut in half. If the volume triples, then the pressure is cut by 1/3. And if the volume goes up by a factor of 10,000, then the pressure goes down by a factor of 1 over 10,000. But the pressure of the gas in the crash pad is at least 1 atmosphere. How can that be 10,000 times less than the gas pressure in the 1-liter can? The pressure in the can must be 10,000 atmospheres. 10,000 times ordinary atmospheric pressure. A can made of steel will explode at about 100 atmospheres. But this Mission Impossible canister mustn't just withstand twice as much pressure as that. Not just 10 times as much pressure, but rather 100 times as much pressure as a steel can possibly stand. But wait, what if the gas that inflates the crash pad is not simply expanding? What if the gas is, in a sense, created by a chemical reaction in the canister? This is how some car airbags work. They inflate under the pressure of nitrogen gas generated by the decomposition of solid sodium azide. But again, there's not enough room in the 1-liter canister for the atoms that must turn into 10 cubic meters of gas at normal temperature and pressure. Thanks to movie special effects, we see an increase in volume. By a factor of at least 10,000. But here's the key point. The key point about reality, the ultimate special effect. When any solid or liquid becomes any gas at room temperature and pressure, a volume increase of about 1,000 is the most we can possibly expect. Or, look at it in reverse. There's no way to stuff 10 cubic meters of gas atoms into a 1-liter canister without crowding the atoms together in a way that violates the laws of chemistry and of quantum physics. But wait, is there yet another possibility? Not the simple expansion of compressed gas, not a fancy chemical reaction that produces gas from a solid or liquid, but how about a physical effect that draws surrounding air into the crash pad? Perhaps something called the Venturi effect, an aspect of Bernoulli's principle, is involved. Look at this. The rapid expansion of an airplane emergency slide is started by the expansion of simple compressed gas. But the high-speed flow of this gas draws in surrounding air to join it. We examined Bernoulli's principle and its so-called Venturi effect in another video. So the emergency slide fills with compressed gas, but even more so, much more so, with local ambient air. 2,000 times more air by volume can be drawn into the slide than existed in the original compressed gas canister. That's good. That's even amazing. But it's still not enough. We need the growth factor to be at least 10,000, not 2,000. Close, but no cigar. And when we consider the obvious need to get the crash pad cover, the plastic skin, into the 1-liter canister, we know it's crazy. The IMF engineers are good, but they're not that good. Mission impossible? Well, crash pad in a can may not be impossible, but that big a crash pad in that small a can sure seems to be.
When you understand the laws of physics, Penny, anything is possible.